This program was sponsored by the Jesse and John Dance Fund. Since 1962, these lectures have been a forum for distinguished scholars of national and international reputation who have concerned themselves with the impact of science and philosophy on man's perception of a rational universe.
Good evening. My name is Marcia Andale, and on behalf of the Graduate School of the University of Washington, it's my pleasure to welcome all of you back to the second lecture by Dr. James Pebbles. Because you are, in large part, a repeat crowd from Tuesday night, I'm not going to repeat the speech that I gave then. However, I don't want us to start without reminding all of us that we are here this evening because of a remarkable gift that was given to the University of Washington over 30 years ago. Through a bequest from the estates of Jesse and John Dance, we in this community for, as I said, over 30 years, have had an opportunity to hear at absolutely no charge some of the greatest intellects that are here with us today. In the last 2 years alone, because of the Dance family gift, we've had an opportunity to hear lectures by Elie Wiesel, Oliver Sacks, Henry Louis Gates, the German filmmaker Wim Wenders, and now James Pebbles. So I think you will agree with me that the Dance family gift is one of the gifts that keeps on giving and that makes this community and this university a very special place to be. Without further ado, now I will turn the podium over to a member of our faculty, Professor Craig Hogan, who is the chairman of our Department of Astronomy, and he will once again introduce Professor James Pebbles.
Thank you, Marcia. Welcome back, everybody. I'm looking forward to another very interesting lecture on cosmology tonight by Professor Jim Pebbles. Jim is a native of Canada, educated at the University of Manitoba for his undergraduate degree, and since then has spent his academic life at Princeton University, where he's now the Albert Einstein Professor of Science. If you attended or saw his earlier lecture, you will have noticed many slides of his graduate students and other colleagues, and we're probably aware that the man behind the shutter must have been in a great many important positions in the history of cosmology, and that, of course, Jim is one of the intellectual leaders of cosmology for its entire modern history since the discovery of the microwave background in the 1960s. He's going to tell us tonight more about the things we don't know about in the universe, and I won't make you wait any longer to hear some of the answers to some of the cosmic mysteries we heard about in his first lecture. So, Professor Pebbles.
Thanks so much, Craig. It's interesting that at Princeton we've had such a named lectureship as this only in the past few years. You have a much longer history of what is, I think, an awfully valuable function of a university. So today, it is research topics in cosmology. I warn you that these are topics of research. That means they are questions without answers. You are going to be left in midair. More warnings. You will read in the media announcements of progress in addressing these questions. I see here that the universe is now thought to be full of inexplicably dense clumps. Next week, it will be inexplicably light clumps, and so on. We're dancing as fast as we can. We are attempting to answer the questions. You do that by making bold guesses, interpretations, which you then check thoroughly and are certainly heavily debated by your friendly colleagues who love to rip you apart by showing how naive you were in thinking that these inexplicably dense clumps are really there. That's the way the game is played. The best rule of thumb I can say for whether you should accept this week's breathless announcement is if it appears in a review article in Scientific American, you can be pretty sure we're all paying very close attention to it. One final cautionary remark. If, as I claimed last time, we have such a well-established theory, why are there all these open questions? The analogy I like is to a building of a bridge under construction. Some parts are thoroughly cross-braced and in place and firm and are established and are not going to fall down. Other parts are kind of questionable. They're hanging there loose. We're not even sure we had attached them to the right part of the bridge. We'll find out when the bridge gets further along. So it is with physical cosmology or any other scientific pursuit. There is a core of well-established knowledge, some of which I told you about last time, that I think is well-checked and believable and is going to stand. There are then many open questions as we attempt to fill out the picture. Here I'm describing some of them. So let us now look at the first slide, if we could turn it on. I will introduce you to one of the great pioneers of astronomy. Could we have the first slide, please? Professor Fritz Zwicky, a Swiss, longtime member of the faculty at Caltech. As I believe you can deduce from this transparency, Zwicky was a man of character. Also deeply inventive, a great leader in bringing us into the modern world of astronomy. He was the first, I think, to, with Bada, to understand that when a star explodes to make a supernova, it's likely to end up as a white dwarf. He led the original searches for supernovae. He was the first, I think, to systematically catalog galaxies at great depth. You see a pile of books down below. I spent quite a few years of my life poring over the data in those books. He recognized, I think among the first, that there ought to be the phenomenon of gravitational lensing. A mass concentration, like the sun, bends light rays. Bending light rays is what a lens does. And just as a lens can focus light onto a point, Zwicky recognized that the masses in galaxies ought to be sufficient to gravitationally lens. Only recently has that effect been discovered. And finally, he gave us a mass problem, here illustrated. Here is a map of the distribution of galaxies in the region of the sky near the constellation Coma. It's, to put it shortly, a galaxy of galaxies. One can measure the velocities of the individual galaxies by the Doppler effect. If the galaxy is rushing toward us, the light is shifted toward the blue, away from us toward the red. So already in the 1930s, Zwicky could collect enough data to get enough velocity measurements of galaxies in this cluster to deduce how much mass is required to gravitationally to hold the thing together, and concluded that there's about 10 times as much mass required as you see in the stars in these galaxies. I guess I should emphasize right at the beginning that that's not a particular crisis. Why in the world should nature be kind enough to put the dominant mass in the universe in a form we readily can observe? But you can clearly see, though, that there is an open issue. If there is all that mass that we're not seeing, there's a wonderful question: how do you discover what the nature of that mass is? If you're looking for a research topic that will lead to a Nobel Prize, here's a good one. Now, there are many open questions. To begin, you could ask the question, well, have people really fairly interpreted the motions of these galaxies to mean that there's a lot of mass there? I think the answer is unambiguously yes. Here's an X-ray image of, in fact, if I remember right, the same cluster of galaxies, showing that there is a uniform glow of X-ray emission across the face of the cluster. One is very sure one understands that this is the glow of X-rays from hot gas, plasma, because in the gas one sees the spectral lines of the common heavy elements. Pretty unambiguous to determine the density of the plasma and its temperature. That gives you the pressure. This sure looks like the plasma is held in place, so you know how hard gravity has got to pull to fight the pressure of the plasma. I'm proud of my astronomical friends to report that the mass you get this way agrees with the mass you get by asking what's required to hold the galaxies in place. A wonderful cross-check that makes us feel confident we have the story right. Another open issue. In computing the mass, we use the old inverse square law that works so very well within the solar system. But this thing is larger than the solar system by some 10 orders of magnitude. That's 10 factors of 10. A spectacular extrapolation. We should be proud that we're only missing by a factor of 10 the computed mass required under the inverse square law. How do we know that the mass isn't, the force law isn't not exactly inverse square, but slightly off? Well, if you believe general relativity theory, the inverse square law is good. If we could test general relativity theory, we would have an answer to the question. The next slide shows Zwicky's lensing phenomenon. Oh, no, I know. I'm the one who's supposed to do that. And can you see the lovely arcs? Lousy images of background galaxies focused more or less by the mass concentrations around in this cluster of galaxies. An image that was a phenomenon that was first detected fairly recently from the ground, this magnificent image, a gift from the Hubble Space Telescope. Those lovely arcs. Now there's a test that one can make. In Einstein's general relativity theory of gravity, the deflection of light around an object like the sun is just twice what you would naively compute using ordinary Newtonian mechanics. That factor of 2 has been checked very carefully for deflection of light around the sun. We are almost in a position where one can check the factor of 2 deflection in this object. It requires a very careful calculation of the amount of mass that ought to be present to hold the plasma together, then use that mass to compute the gravitational deflection of light. Is that factor of 2 present? It looks like it's there, but it's early days. We should keep the options open. There is a chance that the factor of 2 isn't there. If it's not, that's a big signal that we've got the gravity physics wrong. If it is, it'll certainly be strong encouragement to think that the gravity physics is right. So there we sit on this particular issue. I would give odds on that gravity physics is okay and that nature has chosen not to put all of the mass of this system in a form readily available to us. But I would hold a little money back for the possibility that gravity physics is different from what we thought. Just a bit of money. Let's not get overboard. Well, I don't know how to answer the main question. What is the mass in this system? So I'll go on and collect a little more data on the problem by observing that the problem appears in other scales. Here is a photograph of a galaxy. Remember, I called this a galaxy of galaxies. It has a structure very similar to this. The mass distribution quite similar. I remarked last time that in the center of this object there is a jet. Something funny is happening very close in. The next slide shows you that something funny is happening far out. The image you saw last time is concentrated in the center of this very messy-looking image, which was obtained, and I don't mean messy in any pejorative sense, by Chip Arp several decades ago, showing the distribution of light around this galaxy. The contours, lines of constant brightness, or these are contours of constant brightness, indicating that this galaxy of stars is drooping on across the whole photographic plate. It has no edge. It just tribbles on without limit. Not a lot has been made of this, but it does indicate that there is a lot, that the galaxies are rather like icebergs. Most of them is floating below the water. So these galaxies are extended. Now let us look at an X-ray image of the sky and notice that in this full sky image, which has been flattened out so that the plane of our Milky Way galaxy is along this line, we see that our galaxy is a source for X-rays, these X-ray stars showing along the band of the Milky Way. Here is well, if we get it up, well, I know what happened. I put on the attribution and then I noticed I had it upside down. Down here are the Magellanic Clouds, little bits of the Milky Way that seem to have been torn off maybe. Up here, a little smudge. This is the galaxy in this picture. Close-up image shows this. The red spot is the optical image, the bright part, the thing you see in textbooks on astronomy. Here are contours of surface brightness of X-rays. Again, one is confident that these are X-rays coming from hot plasma. Measure again the temperature and the density. You get the pressure. You know how much gravity is required to hold this thing together. And it is bigger by an order of magnitude than the amount of mass you see in the stars, taking account of what's here bright and in the center and what's out here faint and on the outskirts. Again, a mass problem. My bet is that the light in this outer region is nothing but stars. After all, it has about the same color as the light in the middle, where you're confident that the light is that of stars. It's clear that there aren't enough stars of visible kind out in the outskirts to hold this system together. My bet is that it isn't stars, but there's always a possibility that out here there are lots of very low mass stars that don't glow, but of course add up to enough mass to hold this thing together. I'll return to that question in a couple of minutes. I'll remind you next that we're not alone in the universe. Here is the nearest large galaxy to us, the Andromeda Nebula, M31, stretches over several degrees in the sky. It's really looming over us. It's coming toward us at 100 kilometers per second. No worry, I don't think it's going to hit us. But the fact that it's moving, I might as well show you this. It's not going to mean a thing without a whole hour of explanation, but one can compute the motions of the nearby galaxies, this one and other companions. One can get a pretty good and consistent story for the motions of these galaxies. You can check it because you can ask how fast these galaxies are moving now. One gets a good picture for it, but one requires that these galaxies be more massive by a factor of about 10 than is seen in the stars. Again, a mass problem. You're getting tired of hearing about it. Let's go on to a check. How do we know that this isn't mass in low mass stars? Wonderful project, early pioneers on the subject of which are Rich Gott and Bodan Paczynski at Princeton University. I remarked that mass concentrations act like gravitational lenses. Suppose there's a low mass star here. People have taken to calling such low mass stars machos for reasons that have escaped me at the moment. Suppose there's a background star, a bright one you can see. Suppose the little star, low, faint, can't see it in ordinary light, happens to pass along the line of sight from this observer to this star way out in the Magellanic Cloud. If the passage is very close to right dead on line, then you see there will be focusing, and this star will become transiently very bright. A search was mounted for such stars. Christopher Stubbs at this university, one of the major proponents in this search for gravitational lensing events by individual stars. Here, one of the early classical events. One is monitoring the light of a star that's off in the Magellanic Cloud that I pointed out to you in the X-ray image. Transiently, this star gets very bright and then fades away again. You're pretty sure that this isn't a flare-up in the star because at all colors it gets bright in the same amount. That's just about physically impossible to arrange with a flare. One is very confident, I think, these days that what they've seen is a faint star in the foreground passing dead in front of this star in the Magellanic Cloud. A spectacular result when you stop to think that the probability for this happening in a randomly chosen star is about 1 in a million. This is an experiment that could not have been done without high-speed computers and high-speed people who know how to program those computers and build the devices that will look for this remarkable effect. So they found it. There are low-mass stars out there. Are there enough? That's the big question. He keeps assuring me that, well, it doesn't look like it. But he won't tell me definitely no. There's a reason why I think that, many of us think, that there aren't enough of these stars, at least made of ordinary material like you and me, baryons, neutrons, protons, to provide the mass that we need to account for all of the dynamics I've been talking about. It comes from tracing the history of the universe back in time to that very dense early state when it was very hot. When things are hot, you will first, of course, rip the electrons off the protons. You'll have a plasma. Get hotter still, you rip the neutrons and protons apart inside atomic nuclei. You'll have a free gas of nucleons. And you can compute what happens as this gas expands and cools. This will not be on the final exam. I just wanted to indicate to you that it is undergraduate physics work to compute what happens as a very hot cloud of protons and neutrons and the associated electrons and the other particles that give joy to physicists cool and react. And what happens under conditions appropriate to the early universe is you make helium in an amount that agrees with what's observed if the amount of mass in this form protons and neutrons, is maybe, 5%, let's say 10% of what's needed. Well, maybe, no, let me say that again. The amount of material required to account for the production of the light elements by this process is maybe a third, maybe a fifth, depends on who you ask, of what is indicated by the dynamical studies that I have just been describing. The money, therefore, is put on the idea that the dark mass is not this stuff, baryons, neutrons, and protons, but rather some other form. Particle physicists have not been shy in telling us, I pushed the wrong button, that they can easily find particles from the lexicon of modern physics that could be present in great abundance and could solve all of our problems. Many of these particles have the property that they interact only weakly with matter, but they do interact. We have a dark mass problem in our galaxy. There's got to be these particles if they're present anywhere around us. These particles ought to be zipping through this room, and if you have a very sensitive detector, you ought to occasionally detect the scattering of one of these particles in the detector. A search for such particles is underway. A major center for it, south of us, at the Astroparticle Center for Astroparticle Physics, I believe they call it, down in Berkeley. And here is Bernard Sadulay, the leader of this search. If the answer to the problem is new particles that come out of modern particle physics, then we're in good hands. These people will find it. Next topic. Why do we care? First, of course, because there's the open issue. What is this stuff? Next, we'd like to know very much how much there is, because we'd love to know how the world ends. Remember, we have the notion of an expanding universe. That expansion is slowed by gravity. Gravity attracts, it slows the expansion. The greater the amount of mass in the universe, the more strongly the expansion is slowed. If there's enough mass, the expansion eventually will come to a stop, and the universe will come to an end in a big crunch. Now, we should pause and reflect on why we want to know how the world ends. If it's because you deeply care about the future of the human race, then you really ought to be paying attention to problems a little closer to home. In fact, I think that even if it's strictly intellectual curiosity, the answer alone to the question, how will the world end in a big crunch or in a heat death, is to me uninteresting until I can learn its significance in sense of an interaction, an interconnection with something else. That's the great excitement to me, and to most of us, I think, about physical cosmology, the interconnections. A connects onto B, connects onto C, and that explains D. Knowing alone how the world ends is of no interest to me. Well, it would be moving to know. Let us consider some checks on how much dark matter there might be. I illustrate here the expansion time business. Here is the mean distance between galaxies, plotted as a function of time, distance going up, time across. The separation is increasing. Trace back in time. If the universe were expanding at a constant rate, then the distance between galaxies would vary linearly with time, and we would have a big bang back here. If the universe is massive, the mass slows the expansion. That means we used to be expanding more rapidly, and you see, therefore, that the Big Bang happens a shorter distance back in the past. So we have a charming test. If there's a lot of mass in the universe, the time back to the Big Bang will be relatively short. If there's not much mass, relatively long. On Vancouver Island, at the Dominion Astrophysical Observatory, and at the University of Victoria, and at many other places, there are those who study the evolution of clusters of stars. Here's an example from Bill Harris, who's off in eastern Canada, Jim Hesser at the Dominion Astrophysical Observatory, Donald Vandenberg at UVic, showing luminosities of stars and their temperatures, hot stars over here, cool stars over here, in a cluster of stars that you reckon was formed all at once. The mass of the star determines where it will sit to begin with on this diagram. Massive stars sit over here, low mass stars sit over here. Massive stars burn their endowment of fuel more quickly than do low mass stars. They tend to move over to the right and up and explode and become lost to this star cluster. That means that by measuring how all these points are distributed, one has a measure of how old this star cluster is. As you see, it has to be somewhere between, well, I don't know, 10 and 20,000 million years. One has a time. I might just remark that more recent papers than this have slightly lower times. That's because measuring distances in astronomy is very difficult. There is a tendency to push the distances slightly outward. That means that stars of a given apparent brightness on the sky are a little more bright, a little more luminous than you thought. Being a little more luminous, they're burning more rapidly and will die sooner, and therefore the system is, oh wait, did I get that right? Yes, that's right. And so the system is younger, moving over this way. Now, you will have heard many breathless announcements in the paper about the death of the Big Bang. Some of them are concerned with the fact that, according to some estimates of the expansion rate and stellar evolution ages, the stars are older than the expanding universe. That would be a serious problem for the Standard Model. But I assure you it's by no means a pressing issue, because there is considerable uncertainty in measuring these ages, a very difficult art. There's very great uncertainty in measuring this present expansion rate, which of course you can see determines this time scale. And furthermore, you have considerable slop depending on whether you believe the universe is dense or low density, high density or low. The combination means we're still pretty uncertain about this time scale argument. Follow the media with great attention. It will be lovely to see what further progress brings, but follow it with the proper degree of skepticism. Breathless announcements sometimes are not wise. There's another way to play the game. We saw all those galaxies moving around. We could use dynamics to measure their masses, add up the masses, get the total mass implied, and discover whether or not there's enough to slow the expansion of the universe and stop it from expanding. If you do the sums naively, directly, you will find that there is not enough mass by about a factor of 10 to be capable of slowing the expansion of the universe. Now, there's a problem with that method, which is illustrated by Newton's iron sphere theorem. Imagine you have a sphere made of iron. Imagine you stand on the sphere and you drop an apple. According to conventional physics, that apple will fall as if all of this mass were concentrated at a point in the center. Now imagine that I am inside the iron sphere and I have another apple. I let it go. Nothing happens. I float freely. The apple floats freely. I don't see this mass. Mass that's more or less circularly distributed around me is quite invisible to me if it's outside my region. That has led to a notion. This is in the nature of inexplicably dense clumps. Space may be filled with inexplicably low-mass galaxy halos that aren't luminous. And if they're between the concentrations of galaxies that we see, they won't much affect the motions of the galaxies we see. And so in reckoning masses, we will have underestimated, because we will have missed the mass in these low-mass galaxy halos that are underluminous and are in the voids between the concentrations of visible galaxies. Don't blame the authors of this paper. They are only reporting on the prediction of a particular theory for how galaxies form. But they are pointing to a prediction of such theories that, like a high-density universe, space ought to be filled with inexplicably faint, messy galaxies. It's a simple prediction, and one that I'd like to just bore you with a test of. Here is a pie slice showing a strip of the sky in which the angle here is the position along the strip, and the radial distance is the distance of the galaxies away from us. So it's a slice of the universe. The blue dots are from the catalog I showed you of Professor Fritz Zwicky. He, by eye, with his associates, mapped out the positions of these galaxies. Later, mostly at the Harvard Center for Astrophysics, where the distance is measured. Now, of course, because he did this by eye, there is a good chance that he missed galaxies, and maybe he missed these inexplicably faint galaxies that, according to some theories, are present in great abundances between the concentrations of galaxies. That is to say, in these voids. Recent work on faint compact galaxies by Schaumbert and colleagues in a new sky survey revealed galaxies that Zwicky had missed. But notice where they are. They're not in the voids. Still more detailed work by Tracy McGaugh and others yielded yet another set of galaxies even more difficult to pick up, low surface brightness galaxies. They're the red dots. Where are they? With everybody else. Galaxies are like galaxies. The voids are empty. And that means, to my money, there's a good chance that there isn't anything in the voids. They're void because they're empty. And that means we haven't underestimated mass when we've reckoned the motions of the galaxies, and that means that the universe has a low mass density. I would give that about a 50-50 odds of being a correct statement. 60-40, I think. I would be willing to bet that the universe has has low mass and is going to continue expanding forever, according to the conventional theory. But we will see. Let us wait for further checks of this issue. Watch the media. I've forgotten what I was going to talk about next, so I'll subtly check my... Let me emphasize again. It's empty to me to say, yes, we have established that the universe will expand forever. In the first instance, why should I pay any attention to an extrapolation into the indefinite future of a theory I know can only be an approximation to reality? My prediction is that as soon as we know, according to this standard theory, whether it is to be collapse or free expansion forever, smart people will say, wait a minute, I can adjust the theory just a little bit. It will affect none of the standard tests, but it'll affect entirely my prediction of what things will be like in the indefinite future. Instead, let's wait until we establish the cross connections, the cross bracing that allows us to see just what this means. Next issue, I remind you that galaxies like each other, they tend to cluster. I was told that this is getting kind of messy. I have been showing this transparency now for some 2 decades, and it has been remarked that it's getting a little dirty. So I hope you will understand that I cannot bring myself to take the transparency out of the plastic sheet because the machine that made this thing, which was used in early color advertisements, is no longer in existence. And I know of no modern machine that makes such nice, sharp pixels. This is a negative recall. You see the coma cluster of galaxies, the one I've been talking about earlier, right there as a dense dark region. That means lots of galaxies. You see the tapestry of this distribution of galaxies. We asked the question, how is it that the galaxies got distributed that way? For that matter, how is it that mass became concentrated in galaxies? So, a partial answer. Let us make a numerical model for the expansion of the universe. This was done 2 decades ago. You can tell because in those days when you made a Xerox copy of something that was dark, it saturated and became light again. This shows the distribution of 2,000 particles placed at random in a sphere. Computations done by my good friend and associate Ed Groth at Princeton University. Each particle is given a velocity away from the center, proportional to its distance, and adjusted so this thing just has escape velocity. This is a model for a section of our expanding universe. Now ask a computer to trace the orbits of these particles as they move away. Here is what you see at a later time. No, wait, that's not what you see. This is what you see. And I trust you can see that it is clumpy, as you can judge by comparing the original distribution blown up, simply magnified, with the actual distribution. Notice that the distribution has become clumpy. No great surprise. I remind you, as we will see in the next transparency, of a law of physics. May we have the next transparency? I forgot this. Do we have another? Yes. This is meant to remind you that gravity pulls things together, right? You will bear that in mind in your dreams as you will interpret what is happening here. In the original distribution, the points were placed at random, and so there were accidental irregularities. Some spots were more dense than average. Gravity pulled more strongly in those spots and drew material together into clumps, as here illustrated. Oh, I remember why I had that other transparency, and I might as well explain it. This shows 2 examples of distributions of objects. to be compared to this distribution of objects. On the left, nesting seabirds. I am told that they will place their nests so arranged that the distance between neighboring nests is 2 neck lengths long, so the birds can just avoid pecking each other. Other than that, packed as closely as it can be. To a physicist, this is a charming example of a fluid, like water, in which the molecules are placed close together at a very definite distance, but of course not arranged in a crystal lattice. There is no long-range order, although in fact I can see a fair amount of it, but very sharp, close-range order. That is one distribution. Here is another distribution on the right, people on Coney Island. You will notice that people like each other. Where you see one person, you see a lot of people. This, in fact, is a pretty good model for this. And furthermore, so is this. Gravity rather naturally pulls things together in a hierarchy of structure, clumps within clumps within clumps. And remember, I described to you galaxies and galaxies of galaxies, a rather similar and reminiscent effect. An example of more modern computation. We were proud in these days. In fact, in the late 1960s, I spent a month at Los Alamos and was allowed to play with their high-speed computers, the best the world had. It was rather brave because at the time I was an alien, Canadian, and I had to be accompanied always by somebody. It was soon noticed that when I played with these machines, I was totally inept, and so they lost interest in guarding the nation's nuclear secrets. By running the machine over the weekend, I was proud to be able to follow the motion of 200 particles. In this example, there are 2,000. Here, how many were there? Tom?
4 million.
Sorry?
4.5 million.
4.5 million, a piece of cake. Showing a section of a computation of the distribution of mass as it evolves in an expanding universe, and a thing that looks an awful lot like the Coma cluster of galaxies. Rather similar. A beautiful way to follow the laws of physics from postulated initial conditions and discover that under not unreasonable initial conditions, you naturally form things like what we observe. It's beautiful. A couple of lessons. A main lesson, I think, from this computation, though, is very simply described. Let me emphasize it. Here is the character of the original distribution. Here is the character of the distribution after it's expanded a factor of 16. You see that the universe is gravitationally unstable. That is to say, accidental irregularities will grow more prominent. As I've described, the universe, as we see it now, is pretty close to uniform in the large-scale average. It follows therefore, without question, if our theory is correct, that in the past the universe was a good deal more smooth than it is now. It can't have been messy. We cannot have evolved out of chaos. Instead, we've evolved out of very special initial conditions, very close to uniform, and growing more messy or clumpy. It's exciting that we ought to be able to check that, because when you look at a galaxy at great distance, you're seeing it as it was in the distant past, because it takes time for light to travel from the galaxy to us. And so we have a sort of built-in time machine. Things that are far away are seen as they were. And among other things, we ought to discover, people are working to check it, that the distribution of galaxies was a lot closer to uniform in the past than it is now. A partial check, galaxies as they were in the past ought to look young. After all, they can't be any older than the expanding universe. Here is an example of confirmation that that's indeed so. Work from Malcolm Longair in Cambridge, England, and colleagues showing a couple of things. The little blue contours, which I hope you can see, are radio images of galaxies. Remember, I showed you last time that radio galaxies tend to have two blobs, one on either side of the galaxy. Here, even at high redshift, one sees this tendency. Here are images of these galaxies in about the kind of light we can see. And they're more or less like normal galaxies. But here are images of these galaxies in the ultraviolet, short wavelength. They look like galaxies not seen at low redshift. These are messy-looking galaxies in the ultraviolet. We don't have a complete picture of what in the world's going on here, we can only draw one conclusion. These are not like everyday, present-day galaxies. They look a lot like young galaxies, consistent with this picture that the universe is evolving from homogeneity, from a homogeneous distribution to one that contains young galaxies to the present-day old galaxies. I am dying to see the results of a check on how galaxies at great distance are distributed, whether or not they are indeed more smoothly distributed. There are indications of that so, but more work to be done. There's another aspect to this question, how did structure form? Remember that the universe is filled with radiation with very close to the spectrum, that is to say intensity at each wavelength, that is that of thermal statistical equilibrium. Now, the radiation cannot be exactly an ideal thermal equilibrium blackbody radiation because our universe is by no means an ideal heat reservoir. There are hot spots and cold spots, and that must affect, at least slightly, this radiation. According to the standard theory, the effect goes as follows. At the present time, matter and this radiation interact very weakly. But as one goes back in time, the universe becomes denser and hotter, and the interaction between this radiation and the matter becomes stronger and stronger. When our universe was about 1/1000th, a tenth of a percent of its present size, expansion factor of 1,000, volume increasing by 1,000 cubed, 1,000 million, matter and radiation were pretty tightly coupled. At that time, according to this theory, the mass distribution had to be very close to smooth, but of course not identically homogeneous. It had to have ripples that are growing to produce what is present now. These small ripples had to have interacted with the blackbody radiation and perturbed it. We now propagate those perturbations to the radiation forward in time by an expansion factor of 1,000 and predict small ripples in the brightness of this radiation as a function of position across the sky. You will recall a media sensation that was indeed for real and important, the final detection of these wrinkles in space, wrinkles in time as George Smoot calls them, by the NASA satellite called COBE, Cosmic Background Explorer. The blurb on the front of this book about the discovery, the scientific discovery of the century, if not of all time. Well, yes, it was a very important discovery. I guess the best way to put it is there are lots of scientific discoveries of the century, and this certainly was one of them. George Smoot was part of the COBE team. I think that he deserves enormous credit for sticking with an enormously difficult task. In fact, let me first show you what was found, and then we can discuss why I think it was so enormously difficult. May we have the next slide? Here is the sky as seen by the COBE satellite. Dull as dishwater. Smooth to spectacular precision. If we increase the contrast, these slides, in fact, were made under the direction of George Smoot, you find first that you're seeing a little bit of glow from our Milky Way galaxy, and second, that one half of the sky is a little brighter than the other half. That's understood. We are not at rest relative to the universe. We're swooping around, moving under the influence of the nearby galaxies. Our motion causes the radiation to be a little bit blue shifted in one side, a little bit red shifted in the other. This part of the sky is hotter than this. That's a nice thing to see, but not exactly overwhelmingly exciting. If you take out that large-scale variation and then increase the contrast a whole lot more, you see now very, very clearly the Milky Way galaxy, and above it and below it, you see ripples that are now known to be real, confirmed by other measurements. And the exciting thing is consistent to the factor 2, factor of 3 level with what you would expect by the chain of argument I described, tracing the evolution of the universe back by a factor of 1,000 in redshift in expansion, computing the interaction of the radiation and matter at that time, propagating forward to the present. Spectacular that one can go through that enormous loop of calculation and get within a factor of 3 or so of the expected result. Now, why this is difficult is simply that these fluctuations are about at the level of 1 part in 100,000. Spectacularly small, weak fluctuations. I remember after the first year of the COBE flight, George Smoot presented a colloquium in which he described the work being done to detect these fluctuations. At the time, he had only upper bounds, and I remember saying, George, you're really beating your head against a very hard wall. But he continued beating, and of course he beat the heads of his colleagues. And after 2 years, they had a detection. After 4 years, they had a very believable detection indeed that was, as I say, confirmed by other experiments. What's going to happen next? Well, here is another graph showing data and meant to convey not particularly specific information, but rather a concept. One is interested in the degree of fluctuation of the temperature on different angular scales, large scales, small. This graph shows, people tend to plot things in curious ways. Large angular scales are over here, small angular scales are over here. Here are the temperature fluctuations on each angular scale. Here is a part in 100,000. Here, these colored lines are different theories, all kinds of theories to explore. Not all theories are shown on here. Look at all this forest of points. Experiments in progress. You can imagine that after the detection I've described and is described in here, there was a sort of mini gold rush of work to first check on the result reported by these people, and second, to extend it and map out the fluctuations in greater detail. Notice finally the error flags. The detection is there, but marginal. The problem is simple. It's a very small fluctuation, which you're attempting to determine in most of these experiments from observations on the ground through an enormous amount of ambient radiation. A very difficult experiment. It's clear what's got to be done. We need another NASA satellite. Don't bother holding on to your wallet. This is not in the class of space station. Relatively inexpensive. An elegant satellite being built at Princeton University. Principal investigator is Chuck Bennett, who is the Goddard Space Flight Center, just outside Washington, D.C. But on this list, which you can't read, Mark Halpern, UBC, Dave Wilkinson, Princeton, Lyman Page, Princeton, and others. It's going to be shot past the moon to a point such that it will just sit on a line between the sun and the Earth and the satellite. That means that of course, these things can't bear to look anywhere near the sun. They've got to look well away from it. And when this thing is looking well away from the sun, you see, because the sun, the Earth, and the satellite are on a line, it's looking away not only from the sun, but also from the Earth and the moon. The ideal place to be. And in the year 2001 or so, it will map out these fluctuations in great detail. It's going to be just so exciting to see whether or not the fluctuations follow the bumps and wiggles of one or another of these models. Well, there again we stand. I don't know what the experiment is going to see. When we get it, we will have made a great advance that will have led to other questions. And so it goes. That's the way research is. That's the way the research is. You're always left in midair with issues unaddressed. I propose now to have a review, which will be valuable for the final exam in this course. So let us, if we may, show the next transparency. I begin with Ray Weiss, shown at the back end of MIT, pointing to a temporary building built during World War II. Ray Weiss, when he was a young postdoc, spent a year at Princeton University in the group around Bob Dicke. At the time, Bob was very interested in the possibility of detecting gravitational waves. According to Einstein's general relativity theory, when mass is moved violently, as in the collision of two stars or a supernova event, it gives a shake to the curvature of space-time. That curvature ripples away, and with a sufficiently sensitive detector, you could hope to detect those ripples. Of course, you have to be awfully sophisticated in doing this. Trucks passing by will also shake the detector. You've got to isolate the detector to supreme accuracy. I remember elegant discussions by Ray and Bob Dicke during that time when Ray was a postdoc at Princeton University. He now spends much of his time on a gravity wave detector being built at Caltech. When I was taken on a tour of it a couple of years ago, I had a wonderful field of déjà vu. Many of the beautiful ideas that Bob was discussing many years ago being put into very elegant application in this gravity wave detector. I'm certainly watching the media to see what comes of that experiment. Here is a photograph of Bob Dicke the person Ray Weiss came to visit those many years ago. This is a photograph of Bob about 10 years ago. Here is Bob when he was the equivalent of a postdoc, just a year or two out of graduate school, standing on that temporary building at MIT and testing out a radiometer he built, a device that is well adapted to the detection of thermal radiation, such as that would be produced if the universe expanded from a hot, dense state. Here, yet another person low on the faculty food chain at the time, David Wilkinson, who Bob Dicke here had persuaded with Peter Roll, also at the time low on the academic food chain, to build this Dicke radiometer for the purpose of looking for that radiation. Here, Arno Penzias and Bob Wilson using this radio telescope and using a Dicke radiometer to determine that in fact there is thermal radiation filling space-time, a gold rush to see that if indeed this radiation is thermal by measuring the intensity at a whole variety of wavelengths. Here is Ray Weiss. Here is David Wilkinson, now a gray beard in the field. Where's George Smoot? He's in there somewhere. Is that George? Okay. And this group, with wonderful precision, measured the radiation and showed it, yes, it is black body. Here, the competitive group, Herb Gush at the University of British Columbia in Vancouver, readying a rocket flight for the same purpose. Here, his young associates, Ed Wishnow, Mark Halpern, assembling an experiment took 10 years to accomplish, as did the satellite experiment, within 2 months of each other, detect this radiation and show that it is indeed thermal and black body. Now we have the spectrum of this radiation. We're deeply interested in knowing how is it distributed across the space. Here was the first step in getting the irregularities in the distribution of this radiation. Here, I attempted to get Dave Wilkinson together with his young associate, Lyman Page, but they have been on such loose orbits that he was unable to do so. This guy, heavily involved in building that new satellite. This person, Suzanne Staggs, heavily involved in extending the measurements of the intensity of this radiation to still longer wavelengths. What I like about that series of photographs is the illustration that people tend to form contacts, sometimes intentionally, sometimes by accident, sometimes quite against better judgment, that some of these contacts last through the decades and make other connections, in a chain that extends across the field of science and through time, in this case from the 1940s to the 1990s. This is the way people operate. This is the way science is done. Thank you.